we continue, and I hope to finish today with the principal structures related with the full symmetric Toda system and go further. But we need to understand better how it is organized, the R-matrix structure. We started to discuss it, but we need more substantial treatment. So R-matrix structures related with the full symmetric Toda system. And first of all, I'd like to recall you that the full symmetric Toda system is related with the decomposition of the Lie algebra GLN into the direct sum of two its Lie subalgebras, SON. There B plus is the linear subspace and Lie subalgebra generated by the upper triangular generators of the Lie algebra GLN. And SON is a Lie algebra generated by skew-symmetric GI, I less or equal to J. Is it clear? Both subspaces are Lie subalgebras, and GLN is the direct sum of two such subspaces and Lie subalgebras. We introduced a linear operator, the morphism of GLN. So it's a linear operator which acts on this linear space, on this vector space, but it acts as a difference of two projectors. I will denote it P plus, the projector to the subspace B plus, and minus the projector to another Lie algebra. So in a general framework, it is denoted by plus and minus subalgebras. So P plus will be the projection to B plus, and P minus the projection to the SO. And it is always important to say that this is a projector to B plus along SO. You see? And we defined a modified Lie bracket on this linear space xy r, which is 1 over 2 rxy plus x ry, which was a very simple expression in terms of this decomposition. So it is just x plus y plus minus x minus y minus. Plus and minus are projectors to these subspaces and subalgebras. So I just calculated this new operation, R bracket, R commutator, and it appears to have this simple form, and this form manifests that it is also a Lie bracket, a Lie commutator. So such an operation satisfies the Jacobi identity because it is just the difference of Lie operations on two these subspaces. So if we calculate it, we Is it clear that this is also the Lie bracket, the Jacobi identity is satisfied? And that's why we can consider a new Poisson structure. So we consider a tensor symmetric algebra of GLN, but with new bracket, which is given by this Lie commutator on linear functions, and as usual we expand it to all symmetric tensor algebra. So this is our Poisson algebra. Okay, I need some objects. So first of all, GLN has a natural scalar product. So there is a scalar product on x and y, which is the trace of x transposed y. So it's a scalar product, this scalar product on GLN. And we can consider, so we have Euclidean space, we can consider any joint operator. So I will denote star the joint operator. It means that does it mean? It means that R x y is equal to x R y. Okay, I will denote by the action of on Eij. I will introduce its matrix elements JKL, KL, sum over K and L. Okay. R star acting on Ij is the sum over K and L. R, suppose that EKL, something like this. But let us demonstrate this lemma. So you see, Eij is an orthonormal basis with respect to the scalar product. Is it clear? Yes. So that's why the joint operator is just the transposition. It is given by the transposition of the matrix. Transposition means that I exchange the input and output set of indices. You see, so it's quite obvious. The theorem. If we introduce just the Lax operator, GLN Lax operator, so it is with generic elements Eij, Eij. I will use here the symbol of tensor product. It is correct, but it is the same as the Lax operator when we place L is E11, 12, ENN. So you see, it's the same notation, but we understand it as an element of the tensor product of matrices, of the linear space of matrices, and the dual space to the dual space to the Lie algebra. So if we want to calculate its R Poisson bracket, it can be given by the following form: R1 L1 plus R2 1 L with R1 is 1 over 2 R star 1 applied to P12. P12, it is the, remember it's an operator of transposition. P12, EIJ, EJI, and R2 is minus 1 over 2 R star to P12.
In the second bracket shouldn't be one tensor product, right?
Yes, it's L2. So you see,
Yeah.
Just our standard notation for the bracket. It was in your home task. I need some more universal notations. So you see, in fact, then we consider only linear expression in this type. The roles of such elements is very close. So these are generators of the Lie algebra, and these are also the generators of the Lie algebra. So I would like to express this Poisson bracket as follows: as L1 free, L2 free, commutator R. So my statement is that it is the same expression as this one. So you see, it means that there is a commutator only on the third component, commutator in the Lie algebra, but with a changed operation in this Lie algebra. It is the same as to write the Poisson bracket: L1, L2, R. Is it clear, or you need some explanation why it is correct? I prefer to write it. So L13 as the sum of EIJ 1 EIJ. L23 is the sum of 1 EKL EKL. So if you write L13 L23 even with R, it is the same as to write the sum EIJ EKL, the commutator of EIJ EKL, but the commutator R commutator. And by definition, the R commutator of linear elements of these generators of the Lie algebra, it is the same as EIJ, EKL, EIJ, EKL. This is the definition of this Poisson bracket. So it's the same as to calculate the R commutator in the third tensor component. So this notation is a little bit better, so I prefer to use this in what follows. And what it is? What it is? R1 3. I'm sorry. L1 3. L1 3. L1 3. L2 3. R. It is the same as 1 over 2. L R 3. L1 3, L2 3, plus L1 3, R 3, L2 3. Okay? I need another notation or some properties of the adjoint operator. So the properties is the following, that if we apply R1 to L1 2, it's the same as to apply the adjoint operator to the second component. Let us verify that it is true. R1 applied to L1 2 is the sum of R Eij. It is the sum over Ij KL R KL Ij E KL Eij. Okay? And what we remember, the definition of the adjoint operator. So if we sum over Ij here, we get the sum over KL and over KL E KL R star applied to EKL.
CL is just a Lux-metric operator?
Yes, it's just Lux operator, but it is also the matrix of the scalar product. So in dual basis, it is also the matrix of the scalar product, of the bilinear form which defines the scalar product. That's why it acts like this. So I'd like to rewrite this action. So you see here R acts on the second component of this Lux operator. It is the same as to act by the dual operator on the first component. So it is 1 over 2 R1 star L13 L23 plus L13 R2 star L23. And here you see this action can be put off the commutator because it acts only on the first component here. So my operation was to simplify all the expression. So it 1 over 2 R1 star plus R2 star applied to the commutator, but just the standard commutator. But we know this commutator. It describes just a standard GLN plus 1 bracket. this is the same as L1, L2, just GLN Poisson bracket. We know it. It is equal, this is equal to P L2 and equal minus P L1. Do you remember? We calculated this several times. So this is equal to this one. So when we apply such an operator in the first component of this tensor product, if we use this formula to describe this commutator, it means that this operator acts only on this P matrix, not on L2. L2 is in a different tensor component. I will write it, and you please say if you are not satisfied. 1 over 2 R1 star applied to, I will make it in several steps, plus 1 over 2 R2 star applied to minus P L1.
Ask you a question like,
Yes.
what do you, I mean, in the first line, how you express L in terms of R L?
You need to recall the definition that X, Y, R is 1 over 2 Rx, Y plus X, Ry. It is the definition of R bracket.
R bracket,
Okay. Okay, and now I can write it in the following form. That so you see this R1 acts only on P, not doesn't act on L2. So is it correct? It's correct. R1, L2. Yes. It's okay. So it is the same as 1 over 2 R1 star P. In fact, 1, 2 L2 minus 1 over 2 R2 star P 1, 2 L1. So, and up to the change of indices, R2 is minus. So the difference is the following, like this. Yeah. Up to the change of indices, it is the same expression which I have announced.
Why R star acts on the first?
Why R star act on the first term?
Why it's not acting on the L2?
It is exactly denoted that. So R, it's a linear operator on the linear space GLN.
Okay.
GLN. So this expression is in GLN tensor, third tensor power of this GLN. R3 means that it acts on the third component. Okay. Then you use the lemma, this lemma. So if R3 acts on L3, it is equivalent that R1 star act on the first component. Okay?
why this definition of the lax operator, or L matrix in this case, is different from the one that we had in the Poisson structure for the R matrix? We had the contraction for E capital by the components of L, but not with the tensor product.
So it depends. It's the same. It's the same notation. So you see, we can see the matrix with values in some algebra, in some commutative algebra. Okay, it's the same as to write the tensor product of linear spaces.
I mean, the last term.
Yeah.
R2 stars do act on first.
Yes? It comes from this point and from this point. Because before we had R3 acting on L23. After considering this exchange, we get R2 star acting on L23. And it is important that this R2 doesn't act on L13. That's why we can take it off the commutator. Okay? And then we use the knowledge about this commutator. And there are two forms of representing this commutator, this or this, as we like. So then we consider the action of R2 star, we use this form. Because there is here in this formula, the non-trivial component in the second tensor component is only P. L1 is in the first and third component. Okay?
L1 in the first and third component?
So maybe it's better to write L23 and L13. Okay. So these are notations from the Poisson world, and these are notations from the Lie algebras. Okay. Remark and home task 1. The operator R, which is P plus minus P minus, satisfies the in-case condition. In-case condition. It's the following condition. The commutator of Rx, Ry plus R star applied to the commutator, it's the same as R applied to Rx, Y plus X, Ry. Sometimes this condition is called the operator form of the classical Yang-Baxter equation. Amazingly, this condition appeared firstly in differential geometry, and such an important question as the integration of almost complex structure on differential manifolds, describing the complex structure on manifolds. But it makes an important role also in integrable system and algebraic structures behind integrable system. So this equation guarantees that the new operation, the R bracket, satisfies also the Jacobi identity. Okay, but we need to apply this observation to the Toda system. You remember that our linear space is the linear space direct sum of SON, but with the use of our scalar product, we will identify this linear space with its dual, and we will see the dual decomposition, which is the direct sum of the space of symmetric matrices and nilpotent low triangular matrices. So sim is the linear space generated by II and I plus J plus Ji. N minus is the linear envelope of Eij with I greater than 2. I'd like to consider the operation. So I will denote by P B PSO BSO PN PS the projectors to all the subspaces, okay, along the partners. So PB is a projection to the Borel subspace along SO. This is the projection to SO along the Borel subspace. Pn is a projection to N minus along Sim, and PS is the projection to Sim along N minus. Okay. And you remember, I hope, that the family of integrals for the full symmetric Toda system was obtained with the help with the Adler-Kosten-Syme scheme with such a projection to be plus along PSO. Okay, so that's why this projection with projectors enter our consideration. I will consider P B L 1 2. 2 means that I consider the projection to B of matrix entries of our Lax operator. So it's the same as the projection with the help of which we defined the invariant functions, the integrals of motion for the full symmetric Toda system. So this is the projection. But in fact, it's the same thing as to consider P1S of L12. Let us see it. So P2B is the following operator. It maps Eij to Eij if E is less or equal to J. So it's a projection of B plus. So it's if an element is in B plus, the projectors acts identically. But if to Eji, if E is greater than J. You see? Is it clear? We have discussed this last Monday, but if not, I can comment this. Clear? So it means that P to B, so it acts on entries, on matrix entries, on Eij. So now I don't make difference between small and bigger and big generators of the Lie algebra. And there is a sum of Ij. It is the sum Eij. So it acts on the second tensor P Eij. And what is it? I prefer to consider separately the diagonal part. So it is the sum. So it's the sum of diagonal element Ei plus sum over a pair of elements I less than j, Eij plus Eji, Eij.
Projection, why they send Eiji bigger than j to universe, not zero?
This one?
Yes.
Because it's a projection along SO.
Projection of B along SO, right?
Yes. So this project has to map the differences to zero.
So our symbol y
PB applied to Ij is zero. Okay. So it is projection along skew-symmetric matrices. There is decomposition of our linear space into the direct sum of two subspaces. And it always defines the projection to one subspace along the other subspace. And it differs if we change another additional subspace. The projection of, you see, for example, there is a decomposition of JLN as B plus N minus. And we can also define the projection to B plus along N minus. It will act differently.
So PB means keep the part in SON, right?
PB means that SON goes to zero. It's a projection to B.
Again, what is the lower index mean? This 2, P21?
So you see here, I denote L, just L12. So there is the first component and the second component. Okay. And this means that this projection is applied to the second component.
This 2 means applied to the second
Da,
component?
yes,
Okay.
yes.
Could you elaborate why we're not going to make a difference between large Eij and small Eij?
For the moment, there is no difference.
May I ask you why?
So you see, principally, we denote L the sum of Eij. So these are matrix units, and these are generators of the Lie algebra JLN. Our Lux operator is a matrix with values in functions on our phase space. Okay? So if you consider just functions, it is the same as to write just a product. Eij just multiplied by Eij, because functions are commutative. There is no problems to write just like this. But now we consider the Poisson bracket on matrix entries of the Lax operator. And the commutator, the Poisson brackets of these entries, is the same as the commutator in the Lie algebra. Okay? That's why I prefer to use the same letters and to use this tensor notation, because some operations are simpler than you just separate the three copies, and to understand clearly where acts the projector. Okay?
Thank you.
So this is the formula. And this is exactly the symmetric Lax operator we used to define the full symmetric Toda system. So it has some elements on the diagonal, and the same elements over diagonal and under the diagonal. Okay, but I need to demonstrate that it is the same as to apply this projector to the first component. And I need to define what is the projection to the symmetric part along the nilpotent. So PS acts on Eij to 0 if I is greater than j. It's because it's a projection along n minus. Okay? And if we have yes. And what else? PS, if we act on a diagonal element, it is just a diagonal element, and PS acts on Eij plus Eji. It should be Eij plus Eji, because it's a projection to the symmetric part.
So S means symmetric?
Yes, means the symmetric in this. Do you understand that this is the dual space to SO with respect to the scalar product we are considering? Not dual, but orthogonal complement to SO. This is the orthogonal complement to B plus, and this is the orthogonal complement to it. So it is just SON B plus.
PS means the symmetric projection or something?
Yes, it's a projection to the symmetric part along the nilpotent, lower triangular nilpotent. Okay. So this is just the definition, but I need to describe how it acts on the lower, on the upper diagonal, upper triangular part. I need to define PS on Eij if I is less than j. So plus Eji is equal Eij plus Eji, because it's symmetric element of the symmetric, and it's a linear operator, so it is equal to PS of Eij plus PS of Eji. So now I consider I less or equal to j. So it means that this is 0. And this is PS of Eij. this is equal to this one, so equal to P Eij plus Eji. Okay? Now let us apply PS1 to L12. It's the sum of PS Eij to Eij. Over all ij. So it is the sum over I, Eii, Eii. It is 0 if I is greater than j, and it is this element if I is less than j. Eij plus Eji, Eij. So it's the same. So it is not surprising because L operator is the tensor which represent exactly the scalar product, the bilinear form of the scalar product we consider. But we have a straightforward demonstration of this fact. Let Ls be the Lux operator for the full symmetric Toda system. But it means that Ls is the P2S of L12. Then LS is given by this by the same R matrix R1 L1 plus R2 L2. Yes. First of all, let us remark that LS is the same as LR. I'm sorry, P2B or P1S.
I think maybe it's possible to calculate and show it. Maybe.
You see, in LS, the functional part is always in B+. You remember what is LS in the simple case? It is E11, E12, E13, E14, E12, E22, E23, E24, E13, E23, E33. So we work a lot with such an expression for form. So it's symmetric matrix. It means that all entries are elements of the Borel-Lie subalgebra. What do we calculate if we write such an expression? We calculate the Poisson bracket between entries of the Lux operator. And these entries are always the elements of the Borel-Lie subalgebra.
Okay.
The R bracket on B plus is the same as just the standard bracket on B plus. You remember? The R commutator of X is X plus Y plus minus X minus Y minus. So this is B. This is the B plus element, and this is SO element. So if you consider only element from B plus, the R bracket produce, it is just a commutator, just a standard commutator in B. But the commutator in B is the same as the commutator in GLN. So this Poisson bracket for this symmetric Lax operator is the same as R bracket. Okay, now what we know? We know that R is R1 L1 plus R2 L2. I'd like to represent L as its symmetric part and the nilpotent part. So it means that it is the P2. The symmetric part is the B projection of L12 plus P2 on SO projection of L12. And it is the same as P1 symmetric plus P1 nilpotent. So it is just because the sum of projection is the unit, the identity map. Okay. Okay. So I'd like to write here the L S plus L N L S plus L N, the R bracket, it is equal to R1 L1S plus L1N plus R2 L1S plus L2S Sn. But you see in this bracket, if you consider the bracket between Ls and Ln, it will be 0, because this R bracket is such. So it is equal Ls R plus Ln R. Because in this R bracket, the element, so you see here the entries of this matrix are in B, and here the entries of this matrix are in SO. So in R bracket, these two subalgebras commute. It was the definition by our R bracket.
There should be plus note
Here?
the first section.
Yeah. Thank you. But now we can expand this part, the second linear else, into the sum of R1 L1S plus R2 L2S plus R1 L1N plus R2 L2N. And my statement is that this part is equal to this part. Because so this will be the left part and this will be the right part, and both parts are element of GLN and B plus SO L. So if we consider this decomposition of the third tensor component on both parts, this part will be here and this here, and the same for the right part of the of our R matrix formula. So here there are no elements E and B plus. All elements of Ln lie in SO. So if we use this decomposition on the third tensor component of our space, we see that the bracket is the bracket just of the symmetric part has this R matrix formula in terms only of the symmetric part. So I demonstrate the statement, and it guarantees, for example, that let us understand all the corollaries of this statement. Corollary 1. And as I remember, it was your home task. So the I, which are the traces of Li, are in involution. So these are not all the integrals of the full symmetric Toda system. You remember there were many what were called chopping integrals, which were obtained by chopping columns and lines. Yes. But at least all these spectral integrals are in involution using the R matrix formula. Have you such a home task? We will discuss just in several minutes. Okay, and corollary 2. Do you remember we discussed the R matrix structure for the open Toda chain?
Mm-hmm. But I don't remember the formulas, I think.
Okay, firstly, you have the home task 2 is to write down explicitly R1 to find explicitly R1 and R2 in the case of full symmetric Toda system. Corollary 2. We have discussed that the ideal generated by Eij for I is less or equal to j minus 1 in S of B plus is a Poisson ideal. And the phase space of the open Toda chain is S of B plus is the quotient of of the full Poisson algebra for the symmetric Toda system with respect to such an ideal, such Poisson ideal. So, and it means that this Poisson bracket is also valid for the open Toda chain. So it is correct because we just restrict our Poisson bracket to the subspace, to the subspace of generators of Eij with only focused, localized only on the diagonal and on the first upper subdiagonal. But your home task 3 will be to demonstrate that restricting to the open Toda chain L is just R1 plus R2, L1 plus L2. Like this.
What is it in here?
Restricting to open Toda chain. So you see it's a sub-algebra. The Poisson bracket has this specific form. So it can be written with the equal R2 and R1. We have discussed this earlier. Okay. We have 10 minutes to start new subject. During our lectures, you can make an impression that there is only one integrable system.
Why we are studying it so much?
It is very representative. Much of structures appearing in integrable system, they are present in Toda system. So that's why it was our.
I thought it just like
Okay, but we'll discuss Algebraic model 2 and KP and KDV too. But today we say some words about the Gaudin model. Gaudin model. I'm sorry. So in full generality, it is defined in several copies of the same algebra we are talking about, but k times. So it means that there are points and there are spins, and these points, which are defined generally speaking by JLN, but you can consider as U or as O groups, but it can be defined in this general concept. And so the Poisson bracket is the same. So we have phi I, which is the same as the Lax operator, our Lax operator, phi I. It is the sum of EKL with the index I, which correspond to the th copy of our spin space. Okay, and the Poisson bracket is defined on the matrix entries of of matrices phi, and it is defined in an obvious way. KL I E M TS J. It is delta function ij, and then the standard commutator in GL. E K S I delta T L minus E T L I delta K S. Okay. Okay. So the Hamiltonians, the Gaudin Hamiltonians, are written as follows: the sum j not equal to I, trace phi I, phi j, zi minus zj.
These are free spin chains, or?
It is related with spin chains, with the Heisenberg spin chain.
These spins don't have like a physics meaning, or?
Precise meaning?
No, this is a mathematical model. It's not related to physics.
It's absolutely physical. So
Yeah,
Gaudin introduced it in for SL2, which is the same as SO2. So it was just this, some chain of spin interacting particles.
This is not an Ising model or a Heisenberg model. This is just a.
It is the classical limit of the Heisenberg model.
So we are also considering interaction between not close neighbors. Between all the elements.
No, there are interaction between all neighbors. You see.
What is the name of the model again?
Yes, it's a Gaudin model.
What is
No, the name.
Like,
Yeah, we can understand the name. The name. How you spell the name?
Gaudin.
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 Ah,
It's a French name. Gaudin.
Pronunciation is good.
Thank you.
So with this, you cannot solve the three-dimensional Heisenberg model or three-dimensional Ising model because it's not solvable.
It's not the Ising model. Yeah. But so it's some high rank generalization of the model, which is the classical limit of the Heisenberg XXX model. You see? So the rank 2 Gaudin model is a classical limit of some Heisenberg model.
So this phi is a Lux matrix, you said?
The Lux matrix is L of Z. So it depends on a spectral parameter. And this is a new ingredient in our consideration. But sometimes it happens.
This phi operator then is just the R.
Sorry?
What is this phi here?
Phi is a residue of the Lux operator. The Lux operator is a rational function on the spectral parameter Z. So phi, it's a residue.
This
Yeah.
phi and that phi are the same.
Yeah. So you see before we have not this dependence on some additional parameter. So that's because okay, it's always the story between algebraic geometry and Lie algebras. Both these components interfere very importantly in integrable systems. So in the Toda system, there is less of algebraic geometry, more of Lie algebras, and here the accent is different. So there will be an algebraic curve which enter the game, and it is important in solving the system and treating it. So, but we need to understand some properties of the system. Theorem. this Poisson bracket can be expressed in terms of the Lax operator. The Poisson bracket, Poisson structure can be represented by the R-matrix form, and it is a little bit different. Let's see that U is R of Z minus U L 1 LU. And our matrix Z, it is what is called the Young R-matrix, rational Young R-matrix. P12, you know, it is the transposition.
And why this depends only between the difference of the spectral parameter and not on the multiplication of spectral parameter?
It's a statement. I will prove it. Proof. Let us calculate the Poisson bracket of I Z minus Zi K phi K U minus Zk. I K. So first of all, it is 0 if I is not the same as k, because of this delta function. So the matrix L entries from different poles of this system Poisson commute. So it is it is the sum over I Z minus Zi U minus Zi, and here I have phi I, we know what is the Poisson bracket between phi with the same I. Do you remember this formula? And I need also some algebraic expression. Z minus Zi U minus Zi is the same as what? As U minus Z Z minus Zi minus U Zi and divided by U minus Z. Okay? So it means that we have the following: U minus I will write it Z minus U, and then the sum over I sum over I 1 U minus Zi minus 1 over Z minus Zi, and then Poisson bracket of phi I with phi I, which is R12 with phi I2. And this is equal to minus R12, I'm sorry, P12, 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 phi 1I. So this is equal to this, and I will use it up to my necessity. So it is P12 over Z minus U, and when we sum this term with phi 1, it will be L2 of U, and then we sum this with the minus, it will be L1 of Z. L of Z K. Just a moment.
4, I think.
Sorry,
Yeah.
4. So the statement is the following, that if we have such Poisson bracket, then the spectral invariance of the Lux operator, the Poisson commute for all values of parameters. So it's a big family of commuting integrals. You see? Okay, we stop, we make a break for 15 minutes.